So it's my absolute pleasure to introduce Pia Sörensen. It's really such an honor and such a joy to have you here. I'm sure many of you are familiar with her and also with that great YouTube playlist, Science and Cooking on YouTube. I don't know if some of you know it already, but I've spent a lot of time watching it for sure. So Pia is a senior preceptor in chemical engineering and applied materials at the Harvard School of Engineering and Applied Sciences. And she leads Harvard's Science and Cooking program, which includes teaching, research, and outreach programs at the intersection of science, education, and food. And her popular course on food fermentations uses microbial foods to teach principles from chemistry, physics, and biology. She's also the author and editor of several books, including the bestseller Science and Cooking, which I can only recommend as well. And she received a Bachelor of Science in Molecular Biophysics and Biochemistry from Yale, and a PhD in Chemical Biology from Harvard University. So yeah, it's a great honor to have Pia tonight giving us an overview of kind of the main processes of fermentation, the most important microorganisms, the ones you should know, what they do and how they work. And yeah, we will have time for questions afterwards. So I am passing you the mic, Pia. And very happy that you're here.
Thank you, vielen Dank. Ich freue mich sehr, hier zu sein. I speak a little German, but I'm actually Swedish, but my German is not good enough to do all of this in German. So I'm going to do it in English, and I hope that's okay with everyone. But if you prefer to ask me questions in German, feel free, because I think I'll understand it. Okay, so I'm so excited to be here. It's always a pleasure to be in a room with people who I know are already really into fermentation, and where I don't have to convince them that this is really cool. We're sort of already on the same page. So what I'm going to do today, I'm going to share my screen in a few seconds. But what I'm going to do is do what Carla and Frida asked me to do, which is to give a little bit of background about food fermentations in general. And what I think is probably the case is that you all come from slightly different backgrounds. So some of this will not be new to many of you. Maybe some of it actually will be new. But what I'm sort of hoping is that we can all get on the same page at the beginning of these few exciting days. And that we can then kind of use this as a basis that we can then return to over the next few days, and to kind of have something as a common ground that we can sort of work from and disagree with or agree with over the next few days. So let me see, I'm going to share my screen. And what that means is that many of your faces will actually sort of disappear for me. So if you want to speak up, feel free to just like put it in the chat, and I'm sure Carla or Frida will interrupt me, and we'll take it from there. Okay, so you should see this now. And I'm going to click this little video. This is the close-up of something which I think you can probably guess what it is. It's sauerkraut. It's a video by Scott Chmielewski, one of my collaborators, and it's kind of zooming in on what happens with the sauerkraut. I'm going to actually start it again from day one, when the sauerkraut is still green and crisp and the cabbage is kind of, nothing has happened to the cabbage. Then you see that over time, there's a lot of gas forming, a lot of carbon dioxide forming, and the color changes. And for those of you who have made sauerkraut, you also know that the texture changes and the cabbage becomes sort of softer in some ways, but also gains a kind of new kind of crispiness that is not present in the fresh cabbage. So this is the wonder of it all. This is the transformation that happens with microbes. And we're going to spend the next like 35 minutes talking about this. So I want to just, I just want to spend a few minutes just sort of putting you in context where I'm coming from when I'm talking about this. So my background is entirely in the sciences. I spent my PhD doing cancer research. I was pipetting and synthesizing molecules in a lab. And then I got really into teaching. And I kind of discovered that food in general is this amazing tool to get people and students interested in the science that occurs everywhere around us. So for the last 10 years, I've been teaching a university physics course at Harvard, where we do things like we cook various foods and then we use them to study the science. So here is an example of molten chocolate cake and an equation that determines or shows you how quickly the heat moves into the cake over time, depending on various parameters in the cake. And we use this to basically think about the physics. And this course kind of has various sort of spin-offs that we've collected over the years. One of them is a public lecture series where, which some of you may be familiar with, where people in the Boston and Cambridge area come to our lectures and they watch the chefs as they speak about what they do, and then we kind of talk about the science together. And the popularity of this lecture series has sort of then spun off into an online course, which is available for free around the world. You can go on to edX, EDX, and you can take it for free and sort of do the same thing, but do it at home in your kitchen. And then we have various teacher trainings from this. And last year we came out with a book that kind of collects all of this. So this is where I'm coming from. One of my kind of passions over the last few years has been how to teach science through microbial foods, through fermentation. And I have a course on this, but in general, I've just spent a lot of time thinking about it. So just yesterday, I was giving a lecture to my students here. And so what I thought I was going to do is show you some of the introduction that I give to them. And I think that will help us kind of get on the same page. And then we'll take it from there. Okay. So I want to start by kicking off these 4 days with a kind of digital idea for a dinner party. So we can imagine that we're all in the same place. We are all going to celebrate that we're about to kick off this symposium, and we're all going to bring some food. And the only limitation is that you can only bring a fermented food. And so what I would ask you is to just put in the discussion forum all the things that you would be bringing to this party. Yeah, so I see wine, water kefir, bread, sourdough, cheese, kimchi, yes. So lots of things, good. You passed the test because these are all fermented foods. And so you're all welcome to come to the party. Kombucha, pickles, miso, pickled cucumbers, coffee, of course, coffee, you have to have coffee. Wonderful, wonderful. Radishes, fermented radishes. I sense a special interest in radishes. I love radishes too. Wine, awesome, awesome. Okay, so I think we'll get full. Basically, we already have plenty of food to feed us all, and we do that all based on fermented foods. And for some of you, you mentioned some of these things like cheese and coffee and chocolate, but we could also bring wine. We could also bring bread, olives, tempeh, miso, beer. Right here is a picture of Icelandic hakarl, which is fermented shark. So you could easily put together a dinner party only with fermented foods. And of course, I think many of you in this room, you actually know this, but I think it's really important to kind of remind ourselves of how important and common these foods are. So in terms of cooking, if you were to kind of take a bigger step back, in terms of cooking, I feel like there are sort of two kinds of cooking. And the most common one that people think of is to cook with heat, right? We boil things, we char things, we grill them, and so on. And on sort of the contrary to that is to cook with microbes. And in some ways, these are each other's opposites. You could almost say that they're each other's philosophical opposites, in the sense that when you cook with heat, you kill any life that is in that food. Like the chicken that was in this egg here is no longer going to happen, right? That is what cooking with heat does. But when we cook with microbes, we are really doing everything we can to keep these living organisms alive and to make sure they're in their perfect environment, so that the microorganisms that sort of do the cooking for us can live and do their thing. So sometimes I joke with my students and I say, cooking with microbes is really to cook with life, which I think is a sort of a beautiful metaphor to hold on to and maybe think about over the next few days. Both of these, both cooking with heat and cooking with microbes, are ancient practices. As far back as we have evidence of ceramic sherds, we also have evidence of people using those vessels to ferment foods. Sorry, just want to. Okay, sorry about that. So currently the oldest trace of a fermented food has been found in Jihua, China, which is traces of mead. So researchers have basically taken the ceramic sherds, scraped them out, analyzed what the molecules are, and drawn the conclusion that this actually came from fermented honey and fruits and rice and other ingredients that were fermented in these vessels. That was about 9,000 years ago. So that's it turns out that for a long time that was the oldest fermented evidence. But a few years ago, there was a finding in Sweden, actually, southern Sweden, not very far from where I happen to grow up, where archaeologists found this. They found lots and lots of fish bones, all kinds of fish bones. And when they analyzed this, they realized there was the remains of fermented foods and fermented fish. And there were tons of them. And this dates back to about 9,200 years ago. So that is currently the oldest evidence we have of fermented foods. So it goes way back. And you all know this, but really what the reason it is so prevalent and the reason it goes so far back is that fermenting foods really solves what you could call the farmer's problem. Right now in Boston, for the last 2 months, we've had an abundance. The farmers markets here are overflowing with tomatoes and carrots and cabbage and every kind of fruit and vegetable. 2 months from now, there's going to be nothing. I assume it's similar in Berlin. So what do? You figure out a way to save it. And that's basically what fermentation is. You take the cabbage, you turn it into sauerkraut, or if you happen to be lucky enough to have a cow which produces maybe 5-8 gallons of milk every day, what do you do with this milk? Milk goes bad so quickly. Well, you do this, you turn it into cheese, every kind of possible cheese. And you can just look at these cheeses and look at the amazing diversity in flavor that these cheeses have. And that is how to make milk last. Okay, so I want to now take a step back and just spend a little bit of time on what a microbe really is. And there's a few things that that make microbes special. The first one is that microbes are very small. They're about 1 micrometers long. So if you take one of your hairs, you sort of pull it out, and you imagine sort of 1/10 or 100th of the width of that hair, that is how big a microbe is. This picture here is a picture of the tip of a needle, like a needle that you would sew with. These are all the microbes. You can imagine how tiny they are compared to this tip of the needle. Because the microbes are so small, for most of the time that humans were cooking with microbes, we had no idea what they looked like. In fact, arguably the very first time anyone saw a microbe, like a microbe for real, was in the 1600s, when a man called Anthony van Leeuwenhoek, who lived in Delft in the Netherlands, he invented kind of the first microscope. This image here on the right is the first microscope. So it turns out that, so he was a fabrics merchant. He bought and sold fabrics. And it turns out that when you buy and sell fabrics, you're very interested in the microscopic structure of what those fabrics look like. And so if you could have a way to zoom in and look at the thread structure and make sure it's sort of strong and good, then you can make sure you're paying the correct price for your fabric. And so he, because of this, got very into grinding lenses, so these little glass lenses, and got really good at it. And basically, so this up here is a little lens. So he would place the lens here and then look through it. One day, he went out into the canals of Delft, where he was living. This was around the same time that the painter Vermeer was living in Delft. So you can kind of imagine, if you know those paintings, you can imagine what Delft would have looked like at the time. He went out into the canal, took a little drop of water, put it under this lens, and what he saw was this. So you can imagine that if you have never even heard of a microbe existing, you have no idea they're there, and you look into a little drop of water and you see this, you must have just been blown away by what you saw. And what he noticed was a number of things. Number one was he saw, of course, that they're very tiny. The other thing he saw was that they're everywhere. Like, it didn't matter what he looked at. He could just see these little things all over the place. And then he also noticed just the diversity of the microbes. There's these little guys, and there's this bigger guy. There's sort of other things moving around, zipping around. And they all look different and behave different. So lots of them, lots of diversity. So that's one thing with microbes. They're diverse, they're everywhere. The other kind of key to microbes is that they divide incredibly fast. So here is a zoom in of microbes that started out, you see in the very beginning, they started out with just just one microbe, and it divides every 20 minutes. And you can see that over time, even just in like 2 or 3 hours, there are enough of them to fill the screen completely. They're just going. This here really is one of the reasons that microbes are so good at what they do to our food, both when they kind of cook it and when they rot it. They can very quickly take over a food source and just really dig into it and multiply. And even if they're so tiny, the fact that there are so many of them really ends up being visible on a macroscopic scale with your eyes. So if you were to look at this, over time, you would, over some time, get lots and lots of microbes. And sometimes I ask my students this and they get to guess. I'm actually just going to tell you the answer. After 48 hours of doing this, you would have so many microbes that they weigh as much as the entire Earth. Crazy, right? Like if I kept doing this, kept running this video for 48 hours, estimated how much a microbe weighs, then I would get the weight of the Earth in 48 hours. Does that happen? I don't know. Does it happen?
It doesn't?
It does not, right? Exactly. Thanks. It doesn't happen. And the reason it doesn't happen is for two reasons. First of all, the microbes, the bacteria, they run out of food. There isn't enough food there. If you have a piece of bread on your counter and the microbes take over and eat the bread, at some point they're going to run out of bread. They're going to run out of bread before they become as many as weighing as much as the Earth. But that is kind of their potential. That is really, this is to illustrate just how crazily quickly they can grow. So one reason they don't do that is because they run out of food. The other reason they don't do it is because they compete with each other. So this kind of leads us into the second part of the talk, which is where I'd like to just summarize how the main ways that microbes, or I know I'm using the word microbe. So microbe is kind of the collection of it's the common term for very tiny organisms. So bacteria, yeast, even molds count as microbes. So in order to illustrate this, I'm going to ask all of you to take a deep breath and then breathe out. And just keep doing this. Just breathe like you're at yoga or you're meditating. You can close your eyes if you want to. You can try to focus on your breath and listen to me speak at the same time. This is an exercise from my colleague Roberto Coulter, who was the first person. He did this to me once. So continue focusing on your breath, breathing in and out. And as you do that, think about what you breathe in, and then think about what you breathe out. And what I'm hoping you're thinking in your head is that you're breathing in oxygen and you're breathing out carbon dioxide. And there are other gases there, but those are kind of the main things that we breathe in and that we breathe out. And then as you continue to breathe, ask yourself what is happening to your lunch that you had today as you are breathing. And the answer is that, sort of a simplified answer is that your body is taking the oxygen that it's breathing in and using it as a way to convert the lunch you ate into energy. And then the byproduct is carbon dioxide, and that you breathe out and you get rid of. So that's what we do. That's how we humans metabolize, and that's called respiration. Now I want you to continue breathing, and then I want you to just, as you breathe in, hold your breath at the top. So like this. And continue to hold it for as long as you can. How's that going? So my prediction is that at some point this gets difficult. At some point you're going to have to give up. Even if you're like, man, I'm going to show her, I'm just going to hold my breath. You're still, at some point, you're going to be like, I give up, I need to breathe. If you were a microbe, in fact, if you were one of the food microbes that are common in fermenting foods, you would say, no problem. I'm just switching over. I don't need oxygen to convert my food to energy. I can do that without oxygen. And that metabolic process is called fermentation. So that word fermentation is really originally a reference to the way that these microbes get their energy. And over time, it's become a thing that we today use as a way, as something we do to food, right? But it comes from this. So this image here, please continue to breathe. Don't hold your breath anymore. Okay, so what I just say was basically this. There's respiration where you use oxygen to make energy. And then there is, when there is no oxygen around, you use what's called fermentation. And it turns out there are kind of two main ways to ferment. The first is that you use what's called alcoholic fermentation, and then you turn your food source into carbon dioxide or ethanol. The other one is that you turn your food source, which here I've just written as glucose, but it's really any food source, you turn it into lactic acid with fermentation. This is actually the same thing that's happening in your muscles. If you've ever gone running really fast and your calves started to hurt and you were like, oh, I have lactic acid in my, I ran too fast, I have lactic acid, it hurts. So for a very short time you were fermenting, but that was it, you could not do it anymore. So these are kind of, I'm mentioning this because these are the two main ways that we ferment with foods. And once you know these, you will notice that they're all over the place. You will notice that sometimes they interact with each other. But I think sort of understanding them in their pure form is important as kind of, like I said earlier, us all getting on the same page. So let's just quickly summarize alcoholic fermentation. So the most common alcoholic fermentation is done when you make beer, when you make bread, when you make wine. And the most common microbe that does it is Saccharomyces cerevisiae. That's a yeast. Usually when we do alcoholic fermentation, it's done by yeast. There's all kinds of yeast, but this is a very common one. And what they do is they take the sugar, turn it into carbon dioxide and ethanol. And what's so amazing about this is that this little molecule, ethanol, which is just a tiny molecule, is really something that most microbes don't like. So if you have ever hurt yourself a little bit, you've had a scrape or a wound or something on your skin, and you wanted to kind of wrap it up so it would heal nicely, maybe you would go to your medicine cabinet and you would pull out a little alcohol, a little isopropanol, and you would kind of put it on and you would say, oh, now I've sterilized it. Now I've made sure that it's nice and clean. And the reason, of course, is that alcohol kills most bacteria. The superpower of yeast is that they can tolerate just a little bit of it. So this image here on the bottom is, this is a few years ago when a few students of mine, Cindy, Jared, and Richard, they were interested in mead fermentations. So they picked a bunch of strawberries, fermented it over time like this, and then they sampled what the fruit and the mead, the solution, looked like over time. And they noticed that on day 0, they had all kinds of stuff growing on them, on the strawberries. There was all of these gnarly, weird things growing on them. You can see in the middle that already after 24 hours, you are sort of, it's a little bit hard to see, but even after several days, you can see that you no longer have so many microbes. You sort of seem to have one kind. And when you opened up the lid for the Petri dish and smelled it, it smelled just like bread. It was basically the Saccharomyces cerevisiae, which had converted the sugar to carbon dioxide and to ethanol. The other main fermentation is lactic acid fermentations. And this is where little bacteria that are called lactic acid bacteria, because they take sugar and turn it into lactic acid. They basically use the food sources in everything from cabbage, Napa cabbage when you make kimchi, the lactose in milk, the lactose when you make cheese, and they turn it into lactic acid. This is how they make energy. They basically use the sugar and their byproduct is lactic acid. And they usually have names like lactobacillus, lactococcus, or things that start with lacto. So their superpower is that they can tolerate small amounts of acid, so lowering the pH. Most microbes can't do this either. If you've ever made your own cleaning agent, then you know that you can take a little bit of acetic acid, a little bit of vinegar, and you can kind of scrub it, dilute it, and you can use it to clean your kitchen or your bathroom. The reason that works is because acid is an antimicrobial, but these guys are amazing because they can tolerate tiny, tiny amounts of it. Okay, so those are the two main fermentations, alcoholic fermentation and lactic acid fermentation. There is a kind of follow-up to the alcohol fermentation, which is where alcohol is turned into acetic acid. That's another common one, and this occurs in kombucha. I know that Carla told me that a lot of you are big kombucha lovers. So one of the things that happen in kombucha is that little acetic acid bacteria turn the ethanol into acetic acid. So there's kind of another fermentation. But other than that, that's kind of the main two ones. There is a third one, which is a little bit different. And the third one looks like this. So this is mold fermentations. So if you've ever had a piece of bread on your counter and it turned all fuzzy and moldy, then you had this kind of thing going on. The most common food, microbe that is a mold is called Aspergillus oryzae. This is the microbe that is used for miso, sake, amasake, many others. Another common one is Rhizopus oligosporus and Rhizopus oryzae. They look very similar. This one is used for making tempeh. And what they look like if you zoom in is all this sort of fuzz that you see are these hypha, these filaments. And on top, they have these little spore heads. And if you were to look at this black little spore head and zoom in on it, it would look like this picture here. And it's black because it's covered with all these spores, which if you zoom in, they look like this. And this is how they reproduce. This is basically their genetic material, and this is how they reproduce. But this is what it looks like. The reason people usually cook with molds is a little bit different from why you would make an alcoholic fermentation or a lactic acid fermentation. Those both make molecules that are helpful for the organisms that create them, but they are not helpful for anything else. So they kind of outcompete their neighbors. Mold fermentations are amazing because they are basically what people often call little enzyme factories. So what these molds will do is they will release enzymes, and these enzymes will break down the long proteins, the long carbohydrates, the long fats into smaller molecules. And these smaller molecules are small enough so that we can sense them with our noses and with our taste buds. And because of this, they are amazing at producing all these flavors. So some examples of mold fermentations, like I said, is miso, sake, soy sauce, tempeh. All of these, as you can tell, are very, very flavorful, super, super flavorful foods. So far, you may have noticed that we have mostly cooked with sugars, right? With carbohydrates, there was carbohydrates in the cabbage, there was carbohydrates in meat and in bread. This is also mostly carbohydrates in the beans. What happens in a lot of materials that have a lot of proteins and fats is that you get a succession of microbes over time that are very, very slowly also breaking down the fats and the proteins. So this kind of tends to happen after a food has run out of sugars, which are easier to digest. Then the microbes have nothing to eat and they kind of start to use the fats and the sugars instead. And examples of this are a lot of cheeses, a lot of aged cheeses, and a lot of cured meats. So meats that have kind of been going for a long time. And then there is the final kind of fermentation, which is where all of this comes together. And really this illustrates so many fermentations that are out there in the sense that both of these, coffee and chocolate, two of my all-time favorite fermentations, are very complex, and they're also what people call endogenous. And what you mean with this is that if any of you have ever visited a chocolate farm or a coffee farm, you know that you would pick the fruit from the trees and you would just let it sit outside usually, where the fermentation happens completely naturally. Whatever is growing on the thing, it's just sitting there and it's doing its thing. And what's going on a microscopic level is, so something like this, you take the raw chocolate, over time it turns into something like this, and it transforms this fruit, which really tastes nothing like chocolate, into something that actually does taste like chocolate, into the thing. And what this looks like if you were to look at the microbes, is on day 0, you would have a lot of yeast and lactic acid bacteria. And then after a few days, they would have created an environment where the acetic acid bacteria could kind of take over and thrive. And then these guys die out a little bit. And then the acetic acid bacteria live and grow. And then after a few days, there are these spore formers and molds. And now the environment is good for them to grow. So they take over and they grow and they further transform the chocolate. And so over time, you have first a lot of ethanol being produced, then lactic acid, then acetic acid. And then as the molds come in, you get a lot of different flavors being produced. Okay, so I want to make sure we stay on time, so I'm going to cover the rest of this a little bit more quickly. One of the main reasons we ferment foods today is because of the flavor. We no longer have to keep things and preserve them the way we did before refrigeration, but we do it because of the flavor. I think we also do it because of the community and because of the sort of hands-on practice. We do it for all these reasons, but the flavor of fermented foods is tremendous and very interesting. So what I'm going to just show you very quickly is an excerpt from a class that I'm teaching, which basically uses fermented foods, like at-home fermented foods, haute cuisine fermented foods. This is a apple from the restaurant Mugaritz in Spain. It's a very fancy restaurant, but they're experts who do an amazing job at cooking with microbes. And so in this class that I teach, we kind of look at all this and we look at the flavor molecules that are produced and the microbes that are involved in those foods. And then we study the science that goes on in this. So I'm actually going to skip this slide. So just to kind of set up the idea, one of the exercises in this class is that we take milk. We consider this farmer's problem of a cow producing lots of milk. What do you do with it? Well, around the world, there are all these solutions to this problem, which is basically the huge variety of various fermented dairy products. Everything from Greek yogurt to filmjölk, this is what I grew up on, pime, vili, buttermilk, cow milk, all this stuff. What we do in the class is we make yogurt. We make all these different kinds of yogurts. Every student is responsible for their yogurt. Then we study the science that happens in this yogurt. This includes things like lactic acid, pH, the different pathways that are involved, what happens to the proteins, and so on. Then we invite a sensory analyst. Her name is Maya Grace. She's an expert at trying to capture what do our senses really understand when we eat foods. And she turns us into a flavor panel. So this is students tasting all the different yogurts, taking notes and trying to analyze what they taste like. Then we put all of this information together. And here you can see just how even a simple material like milk, like all you added was milk and microbes, and yet you get hugely different flavor profiles. So one of my favorites is the Vili and Mazzoni, which taste like old stable. And obviously a lot of them are sour and acidic, but you also have a lot of sort of bitter and sour, butter, smooth, thin. This may not seem so interesting to you, but if you've spent an hour carefully tasting yogurts, then you stare at this and you're like, oh my God, what do they, no one agreed with me that this one was bitter, but I thought it was bitter. So this is what we do. And then we talk about flavor in a very big picture. We talk about the multisensory aspects of flavor. And we do this together with my colleague, Ben Hogue, who is a musician and who has worked with various restaurants to create sensory experiences that really include all of our senses. And we compose some music to go with the yogurt. This here is a piece of music that a student composed to illustrate Greek yogurt. Oops. And it sounds like this. Okay, so that is the sound of yogurt. You can imagine the popping sound and the slight acidity. Then we take our yogurts down into the lab and we do liquid chromatography and mass spec. We end up with this crazy plot, which basically shows you all of the flavor molecules that are in the yogurt. And we analyze it and kind of use this, what's called a PCA plot, to basically analyze all of those molecules. And we see that the Bulgarian, the Greek yogurt actually should taste kind of similar. The Mazzoni and the Vili should also kind of taste similar based on the flavor molecules, whereas some of these taste a little bit different. Then we go and we look at all the other molecules and look at the main ones in more detail. This is a list of all the molecules that are there. Propionic acid kind of smells a little bit cheesy. These pyrazine and pearl are a little bit nutty. And we try to basically compare our sensory experience to the flavor molecules that were actually in the yogurt. Then we go and we sequence the microbes that are actually in the yogurts and we look at what's there. And this is the findings from one of the yogurts. Bifidobacterium is the main one. Lactobacillus acidophilus is another one. And we compare this and look at how the microbes influence the flavor and how the flavor experience is matched by the molecules that are there. Okay, so that's an example. And I'm actually going to wrap up by saying two things. One is that if this is interesting to you, then we have an online class on what's called Harvard X, which is with me and my colleague, Roberto Coulter. He's a microbiologist. It's completely free. There is another run starting in October. You can just go in and do as much or as little as you'd like. So this is there if you're interested. And then if you're interested in the book, this is what it's called, Science and Cooking. It should be out there, should be available in Germany as well. And finally, I want to just thank, first of all, my students who have kind of been along with me for the ride as I've been thinking about fermentation. They always come up with amazing questions that make us figure things out together. I want to thank Mai, Patricia, Roberto, and Casey for working on these classes with me, the visiting chefs and speakers and the field trips host, and then my schools for supporting this adventure. So I'm going to stop sharing, and hopefully you're still there. It's nice to see you again. And let me know if you have questions.
Thank you so much, Pia. Thanks. A big round of applause. There's a little button for that. Yay. Thanks so much. That was really helpful. Yeah, I spent a lot of time with fermentation, and I always kind of was hoping to find such an overview like of what the different microorganisms do. And yeah, that was really helpful. So now we have time to ask Pia some questions. So feel free to write some in the chat or just to raise your hand. I have a few questions as well. So I'm just going to start. So one thing you didn't talk about so much in your presentation was your relationship with chefs. I know that last time we spoke, you just spent a few days at NOMA. And I think the director of the NOMA fermentation lab was visiting Harvard this week, right? So
that's correct.
Maybe you can tell us a bit more about how you work with chefs and what they bring to your work and vice versa.
So I think first and foremost, what chefs have added to my work is the inspiration. I think there's sort of traditional fermentations which have been done for millennia. Those are the sauerkrauts and the breads and the wines and the beers. But then there is all these new ways to use fermentation. And that is often done these days in haute cuisine restaurants, in very fancy restaurants. So places like Mugaritz in Spain, David Chang here in the US. Noma, of course, is a huge inspiration, I think, probably for some of the people in this group as well. So very much I've used it as a point of inspiration, both as a way to involve students in being very creative with fermentations, but also just as an inspiration for my own work. So some of the projects I have going right now is a collaboration with one of my students who is at Restaurant Alchemist in Copenhagen. She is doing a project on miso and a flavor called kokumi, which for many people is thought that it's kind of the sixth taste. So there are the 5: sweet, sour, salty, bitter, umami. And then there are kind of various contenders for what could be a sixth one. And kokumi could be one of them. So that's one example.
Okay, didn't know about that one. And how did it start also that Harvard got interested in fermentation and cooking and chefs? Because that's not something that's always has been, right?
Yeah, it's true. Harvard is not really traditionally a food space at all. They do all kinds of other things very well, but food has not been a thing. And it really started when this course started, the science of cooking course started about 11, 12 years ago. And then it was entirely as a way to teach, right? It was a way to teach physics, chemistry, biology. And then what happened was that I got so interested in fermentation, and my background is more in biology and microbiology. And so I thought fermentation is this perfect tool to teach, but there is also, it's a very new field. So it's also a wonderful place to do research. So it's kind of developed over time, but really teaching was kind of the driving force behind it.
And can you tell us more about what's being researched at the moment? It's a big question, but I'm just curious.
Yeah, so one of them is the kokumi thing I mentioned. We also have a project trying to understand ancient fermentations, so bread fermentations, and how understanding the material that bread is, how can that inform how we think about how people actually made bread. So that's one one project. There is currently another project on amazake, trying to make amazake in novel ways. So it's a little bit all over the place. Yeah.
Okay. Yeah. Exciting. Do we have any questions from all of you guys? I think Friederike raised her hand. No? That was by mistake. Okay. Anyone else?
I have a question.
That's the same question, so.
Okay.
I have a kind of comment question, maybe. First of all, thank you, Pia, so much for your presentation.
Oh, now you're muted.
Oh, sorry. Not sure how that happened, but it has to happen at least once in the evening, right? So yeah, I was saying I'm so not a science person. I must admit that to the group. And so I think that I'd always thought about fermentation as something that we do to food. And then as you were speaking, I was thinking it's actually, I never thought about it as something that is just happening naturally all the time. And then at some point I thought, so then this is food when it wastes on our counters or something is just fermenting. So it's getting better maybe, but then it's not better for us. So there was lots of thoughts in my head as you were speaking as a non-science person. So that was an interesting takeaway. But also, as you mentioned, these are things that our ancestors have done. Fermentation is the way that we've always preserved food. And like these things are often passed down through tradition and story rather than knowing the science all behind it. And so, yeah, I'm kind of like thinking about that and how interesting it is that you and your students do all the science behind it and how you came to it on teaching, like how you could teach through it. But also, yeah, this usually comes through storytelling and just thinking about the differences of that.
Yeah. Thank you for adding that perspective. That's really, it's people often ask these very specific questions, but I always wonder what goes through people's heads as they hear this, and that's helpful. That's so great.
Is it? Because I know it's so random, but I mean, I
No.
also just wanted to share a bit. I don't like I said, there's not really a question in there, but that's kind of what was going through my head.
Yeah. So one thing that strikes me as a scientist is, and I think this is true for fermentation, but it's also true for a lot in cooking, where so much of it is passed down by word of mouth. And there's kind of these like, oh, you do this and then you do this. And I think what is striking for me and what I try to highlight with my students is that there often then actually is a scientific reason for why you do that. Like there's a reason the story was passed down as it was. There's a reason you should, knead your cabbage to release water. And the reason is that way you can submerge it and you can have an environment with no oxygen so that the right microbes can grow there. And so what I think is fascinating is that these are completely connected, right? Yeah. And I also like what you said about whether the food is turning good or turning bad, there is still a fermentation going. And some microbes are still happy. They don't care that you like one better than the other. So, there's still microbial life there. So there's a lot of philosophy there that I think is fun to think about.
Yeah, we're going to dive into the philosophy part right after. Looking forward. Are there any more questions? I have a very specific question, like super specific. I've always been wondering why it's called lactic acid when it doesn't have anything to do with lactose, right?
Well, it sort of does, actually. If you were to look at the lactose molecule, you could even just like Google like lactose and then Google lactic acid and you compare the molecules, you'll see that they really have one end of the molecule will be changed. And basically for the lactic acid, you've added a little acid at the end. So they actually are connected, even though you wouldn't necessarily think so. Yeah.
Okay. Okay. Yeah. Yeah, because you always hear, people wondering if it's vegan, if it's lactic acid, and questions like that. But okay, yeah. Right. So, any more questions? It's now or never. Don't be shy. Annette, you had some questions, but it was mostly about translation, right? Okay, so that was that got fixed. So if everybody's happy, then we will just take a short break. Sammy is...
Oh no, I saw someone's hand. Mario?
Okay. Yeah, Marius? Yeah.
So I was just wondering, you said that microbes break down sugars and carbohydrates, but as soon as they run out of it, they start to break down fats and proteins as well. Is it just that they do this as soon as they run out of carbohydrates, or do they already start doing it before?
I think it depends a little bit on the microbe and what their preferences are. But in general, carbohydrates tend to be more accessible to the microbes that are in food fermentations. And also what tends to happen too is that over time, when the proteins and the fats are being broken down, part of that is not microbes. Part of it is just aging. It's just naturally what happens to molecules over time as kind of, as life hits them, they just naturally start to break down. So they're partly parallel, but they're not sort of sharp boundaries like that. Yeah.
Okay.
Good question. Great question. And
also I was wondering more about Kukumi, how your research looks with Kukumi. And what it actually is, or how.
Yeah. So it's very interesting to me because it's in a way very subtle. I think for all of us, if I give you something sweet, you're all going to say this is sweet. And maybe some people can't taste sweet, but most people can, and it's very clear. Same with salty and same with bitter. Kukumi is thought to have a flavor of, it's often referred to as mouthfulness. Sort of a sense of kind of filling your mouth and coating your mouth. So it's almost, in some ways, it's almost like a texture, like a texture as opposed to a flavor. It's caused by very short peptides, which is essentially small pieces of proteins, like 1 or 2 amino acids, sometimes 3, 4. And the idea is that they, in some way, it's not clear what they interact with, that's not known, but that they give that sensation of some kind of mouthfulness. The thing that's tricky with studying it is that it is a subtle flavor, and it's not necessarily a flavor that we are used to picking up on. There's some evidence that this is more common in Asian cuisines, where you would have that more, where you have a name for it. So much of flavor is also like, do we have a name for speaking about the thing that we feel? So it's a very complex area, but that is what makes it interesting to figure out.
Yeah, a lot. So it's more like a mouth feeling.
Mm-hmm, mm-hmm.
Or it's the other tastes.
Mm-hmm.
Okay.
Right.
Interesting.
I have maybe one last question. Can you just give us your favorite books or podcasts that you love to listen to, or like people in the field of fermentation that you would like to drop?
Yeah, I happen to have them right here. I'm just going to pull them up. So one of my favorite ones.
This is not an ad, by the way. I really just want to know. No one's getting paid for this.
No, absolutely not. One of my favorite, and I actually just happened to have them here because I was using it last year. We were teaching remotely because of the pandemic, and so I happened to still have all my stuff that I was using when teaching right around me, which you can't see. But this is one of my favorites. This is from Art of Fermentation with Sandra Katz. Another favorite is the Know My Guide to Fermentation. I think those are the main books that I have here. Yeah, but another one, there's a fantastic seminar series called Fermentology. It's run by a group at North Carolina State University. One of the people is Rob Dunn, called Fermentology. You can Google it. Some of the speakers that are going to come after this have books, actually. Rich has a book on koji, which is amazing. But I think those are the main ones. There's so many resources, actually. There's so many good books. But those are kind of the ones that come to mind and that I sort of use on a daily basis, or not daily, weekly basis.
And also I saw some upcoming dates on your lecture series. Can you maybe tell us how people could join or watch the recording?
Yeah.
How it works? Yeah.
Right. So we have this public lecture series, which happens every Monday night at 7 US time. So that's awfully late for you guys. But if you happen to be up, we do run it live on Instagram. So if you go to Cy Cook Harvard, I can write it in the chat, Cy Cook Harvard. That's our Instagram. And so then you can watch it live. We also do plan to edit more high quality footage and put it up on our YouTube channel, but those are not up yet. And usually there's a delay of like 4 weeks or so. Mm-hmm. If you come through Boston, you should come in person and say hi. I realize that's a little tricky these days. But the director of fermentation of NOMA was just there 3 days ago, on Tuesday. So that one is actually up on Instagram live, if you wanted to look at it. So that I recommend. They're amazing.
Okay, great. Thanks so much for that. Thank you for your time. Thank you for joining us.
Thank you. Thanks for coming. It's great to see so many people.
Yeah. So goodbye, Pia. I mean, you're welcome to stay, of course, if you're interested. And now we have a short break, I would say 10 minutes, because we're running a bit behind, but that's all right. So we meet back at 6:15, German time, Berlin time. And see you soon. Okay. Bye.
Thank you, Pia.
Bye. Thank you. Thank you so much, everyone. Thank you, Carla. Thank you, Frida.
Thank you.